Welcome to The Explainer. Today, we're diving into the sheer industrial magic of turning raw fuel into powerhouse energy. It's this incredible behind-the-scenes journey of physics, chemistry, and just massive machinery that has to happen before a single kilowatt of electricity is ever actually generated. Think about it for a second. How exactly do we take a massive, wet, clunky mountain of raw fuel and transform it into this explosive, highly efficient powerhouse of energy? It's definitely not as simple as just tossing some rocks into a fire, right? We're looking at a staggering engineering challenge here that requires a really intense, how-it's-made style physical journey to solve.
Here's our roadmap for this journey. We'll start by upgrading the raw fuel, tackle the very real dangers of storage, move into the great crush, look at grinding it all down to a powder, and finally, figure out how to move the mountain.
All right, part 1, upgrading the raw fuel. Let's look at the chemical preparation.
So, before we even think about baking the fuel, we actually have to prep it. We add catalytic materials like lime to pump up the ash fusion temperature. This is super important because it stops these rock-hard clinkers from forming inside the combustor later on. Once it's prepped, we literally bake it. Step 1 is torrefaction. Think of it kind of like a dark roast for your morning coffee. It's a mild pyrolysis process that happens between 200 and 300 degrees Celsius in an inert gas, so we avoid oxidation. And it turns the material a rich, dark brown. Step 2 takes the heat way up with carbonization. We're talking 500 degrees Celsius here, which outputs charcoal and gaseous fuel. And hey, for those super low-grade wet fuels, the ones with over 90% moisture, modern engineering steps in with hydrothermal carbonization to pull out that charcoal.
Now, let's see what happens when we crank the heat to the extreme. If you've ever heard the industrial term coke and wondered, okay, what actually is that? Well, here's your answer. Coke is made by devolatilizing bituminous coal completely without oxygen at a staggering 900 to 1,000 degrees Celsius. I mean, that is seriously hot. The result is this hard, porous, gray fuel boasting a massive heating value of 29.6 megajoules per kilogram. It's mostly used in the heavy-duty blast furnaces of the steel industry. And if we're working with lower-grade coal, a caking process gives us what's known as semi-coke.
And you know, this perfectly highlights exactly why we can't treat all fuels the same way. Take a look at biomass versus coal. Biomass is incredibly stubborn. It holds on to moisture and is hygroscopic, which is just a fancy way of saying it actively absorbs water right out of the air. That makes it ridiculously tough to grind. Coal, on the flip side, is naturally brittle. It practically wants to shatter. And that is actually perfect for us because our ultimate goal here is to grind it down into an ultra-fine pulverized powder. Why go through all that trouble? Because pulverized coal burners can achieve a massive power density that actually rivals gas burners. It's a total game changer.
Moving on to part 2, the dangers of storage. How do we safely manage all this fuel?
Now, storing giant mountains of potential energy, that is a huge safety hazard. The absolute most critical thing here is managing trapped heat. See, when coal just sits in a massive heap, it naturally soaks up oxygen from the atmosphere, and that generates heat. If you pile that heap too high, you end up compressing the bottom layers, which closes up all the little gaps where that heat could normally escape. The terrifying result? Spontaneous combustion. Yeah, the pile literally sets itself on fire. To stop this, engineers are incredibly strict about keeping heap heights to a maximum of 10 to 12 meters. Some modern plants even go as far as using underwater storage or protective CO2 gas blankets. Oh, and the golden rule of fuel handling? Never, ever store pulverized coal for an extended period. It is just way too explosive. We only crush it down to that powder right when we're actively handling it.
Which brings us to part 3, the great crush. Let's talk about increasing that surface area. So we know how dangerous the powder can be, but why do we absolutely need it to be so small? Well, it comes down to simple physics. Drastically reducing the particle size massively increases the exposed oxidation surface area, and that translates to way higher thermal power in the furnace. To get this initial crush going, we bring in the heavy machinery. First, we have jaw plates. These use a hydraulic linear movement, basically a converted rotary motion, to physically smash the coal. They get the job done, but they definitely have limited capacity. Then we have the double roll crusher. This beast gives us medium to large capacity. It relies on a continuous rotating motion that is incredibly efficient, though, as you might guess, it does come with a heftier price tag.
All right, part 4, grinding to a powder. Time to transform these rocks into dust.
To actually hit that gas burner level power density we talked about, we have to take those crushed rocks and transform them into a microscopic powder. Enter the pulverizers. First up, the ball mill. Picture a massive, heavy-duty drum filled to the brim with steel balls. It operates at a really slow, lumbering speed, only about 10 to 20 RPM, just constantly tumbling those heavy balls over the coal to crush it down. It has a massive capacity, but here's the catch. Its output is entirely dependent on time. The maximum size of the powder that manages to escape is strictly determined by the diameter of the holes built right into the drum's walls.
Next, we really step up the speed with the roll and bowl mill, which cruises between 40 and 225 RPM. Honestly, this machine is brilliant. It has these rotating parts, the bowl at the bottom and more at the top. As it spins, it cleverly uses centrifugal force to fling the heavier, uncrushed coal pieces away from the center so they get ground down further. At the exact same time, a perfectly tuned blast of air sweeps through to push only the finest coal powder out of the mill and send it straight onward to the boiler.
And then, oh man, we have the hammer mill. If the ball mill is a slow, tumbling drum, the hammer mill is basically a giant, high-speed industrial blender. This thing spins at a blistering 900 to 1,000 RPM. It doesn't just crush the coal, it absolutely shatters it on impact using sheer kinetic energy. It's violent and highly effective. And to control the final particle size coming out of a hammer mill, engineers just swap out the sizing sieve. Simple but incredibly effective.
Finally, we reach part 5, move in the mountain, handling all this massive fuel.
Okay, so our fuel is perfectly pulverized, but we've got one last major hurdle. Continuous, large-scale transport straight into the roaring boiler. To pull this off, engineers deploy a whole arsenal of conveyors. We've got screw conveyors, which look exactly like giant rotating corkscrews, and they are fantastic for moving material up steeper angles. We also use flight conveyors. These swap out your traditional belt for a chain and flight plates, again, to tackle those steep inclines without everything sliding backward. But when it comes to the absolute smallest, finest powder particles, we rely entirely on belt conveyors. Why? Well, a screw conveyor inherently has a tiny little gap between the rotating screw and its fixed housing. And that super fine powder, it would just slip right through. Now, what about when we need to lift this sheer volume of fuel straight up into the air? That's where the bucket elevator comes in. Unlike a skip hoist, which just uses one large bucket for batch feeding, the bucket elevator is an ingenious, continuous mechanical loop. It just scoops, lifts, and dumps in an endless rhythmic cycle. This guarantees that the boiler absolutely never starves for fuel, keeping the whole factory flow moving without a single interruption.
And finally, to actually manage those massive shifting heaps of fuel way back in the storage yard, we use the grab bucket. Sure, it's limited to a batch feeding mechanism, but what it lacks in continuous flow, it makes up in sheer flexibility and freedom. Think of it as the giant mechanical hand of the whole operation. It reaches out and dynamically moves tons of material back and forth between multiple coal heaps as the plant's daily needs inevitably shift around.
It's pretty incredible when you step back and look at it, right? We literally just traced a journey from damp, clunky, raw chunks of earth all the way to a scientifically perfected, pulverized cloud of explosive energy. So, I want to leave you with this thought today. The very next time you walk into a room and casually flip a light switch, will you think about the massive, hidden engineering journey? The crushing, the grinding, the careful chemistry that actually made that instant illumination possible? Thanks so much for joining me on this explainer, and keep questioning how the world around us actually works.